four of the same type of drum, just two different ways. So is a drum set.
Hello and welcome back to Calculus 3 with section 11.9. Yeah, I can't speak today, so I'll just mime the whole thing, and let's see how that works. The idea is to learn about curvature. Curvature is going to be a quantification of how fast the vector r, which is our position vector, turns. And we are going to develop the formula for it and use it, obviously. So we are going to define the formula through one concept, but we'll use a completely different formula to compute, because definition is easy. The form for definition is easy to understand, but it's really difficult to compute. So we'll run two formulas, and we'll obviously use the one for computation to calculate things. We start by first remembering, and this is very important, the unit tangent vector definition. Which was given as the derivative of r divided by the magnitude of vector r. You can also call that velocity divided by speed. So whatever formula you want to use. So velocity divided by speed makes more sense for unit tangent vector, because we said that if you have some kind of curve in 3D space, the tangent vector is the one that tells you the direction of motion along that path. But now I want to measure the curvature, and the way we do it is we use parametrization of the arc length, which is not too friendly for computation purposes. So if I observe a curve and I pick 2 points, the tangent vectors, the unit tangent vectors there, show the direction of motion. And the part that is traveled across is change in s, which is the arc length, which is the length of the path that the object passes between point 1 and point 2. So the curvature is defined by the change of the tangent vector in respect to the curvature, in respect to the arc length. So I hope that you can see that the tangent vector at the first location and the tangent vector at the second location has a different direction. They're both unit tangent vectors, so their magnitude is always 1. But everywhere on that curved path, the only thing that is changing is the direction of the tangent vector, and that changes in respect to the curvature of the arc length, right? So arc length, so we will say that the curvature k, which is quantification of, we'll talk about that, is given as the magnitude of the derivative of the tangent vector in respect to the arc length. Now this is our unit vector. Now something like this, we're not too keen on computing, so we are going to use this to define, because it's easy to understand. You can see the arc length there, change in s, and you see that the tangent vector is changing its direction as the point travels from position 1 to position 2. So we are going to define curvature by, let R describe a smooth parametricized curve if S denotes the arc length and vector T is our good old unit tangent vector, the curvature K in respect to S is going to be dt ds. You will see that the more the path curves, the larger value K. Now what I want to do is I want to recast this formula from being parametricized in respect to parameter S to parameter T, because our function which describes the vector valued function which describes the path, describes the line that where you want to measure curvature, is in terms of parameter T, not in terms of parameter S. So you can, those of you in honors option, please consider the manipulation. It's 2 lines of how to get from the definition to having curvature expressed in terms of parameter T. That's on page 842 for quick reference. The formula which we are going to use in class is going to be magnitude of derivative of the unit tangent vector divided by the magnitude of r prime. So this is the equation for curvature, to calculate curvature. One of the extra problems for honors section could be to derive the later equation from the previous one using those 2 steps that are outlined in a textbook. So that's one of the possible problems. And another one would be yesterday's length, arc length, and so on. Yes?
Would just the normal class options have to do any derivations?
No proofs and derivations for the vanilla Calc3. All right. So, as I said, the sharper the turn, the larger value of K, which tells us that the straight line should have 0. Straight line has a 0 curvature. So how about we test that in a problem which will review your knowledge of lines, and then we toss in the new concept here. So here is a problem for you to work on right now. Now you can, talk to people sitting next to you, work in groups. So first, find the equation of the line through 1, 2, 3, and 7, -4, 5, whatever, and show that its curvature is 0. So this is a possible exam question if you want, because you have to use the equation of the line to figure out what is the line, and then you will get parametric set there, you know that hopefully by now, and then use the formula which you just learned to show that its curvature is 0. Alright, so no pressure, we have 18 seconds, go. Just wasted one, go. Oh, see you next week. Maybe. What just happened? What? I never like to do this on the board.
What's that? I can do like the first part, but that's about as far as I've gotten.
And then you can just do the second part after.
Yeah, Evan, do you
Tag
want
off with that.
Red marker works well. And just go here.
can't tell.
Yeah, okay.
This comma, this comma, this.
Just T times one. Magnitude T times one. T times zero.
Now take it derivative the r prime. Great. Now, hey, unit tangent vector is. Yeah,
Wait a minute. Yeah.
Unit tangent vector is this divided by its magnitude, right?
And then I divide this by that. Or divide it by.
That's your unit tangent
That's
vector.
my unit tangent. Good. And I'm dividing all this.
You actually find this they're all not.
Cool.
I don't know if that's legible or not. What?
So we start by creating a vector v, which is the third-dimensional slope for the line, by simply subtracting coordinates. 7 minus 1 is 6, negative 4 minus 2 is negative 6, and 5 minus 3 is 3. And we have a point 1, 2, 3 as initial point. So x equals y equals z equals parametric set for the line. We put the point down 1, 2, 3, and then plus 60 minus 60, and then plus 3t. So this gives us the parametrization, and you can immediately take the derivative, because you know that creating a unit tangent vector will ask you to find this derivative, which is 6, negative 6, and 3. And to create a unit tangent vector, you divide r prime with r prime magnitude, which in our case is 6, negative 6, 3, divided by the square root of 6, that's 36, that's 72, that's 81, right?
72
Plus 9 is,
plus. You're doing it wrong, but you're getting.
It's
You're fine.
These
These are supposed to be 6, negative 62. He's doing it a little bit different.
Two.
He's doing it
Did I
different.
do my
5 minus 3 is 2.
5 minus,
5 minus 3 is 2.
that's what I said. Oh, what do I have? Oh, I have 3.
That's what they said. They said
Yeah, no one is paying attention here.
I caught it.
When?
Just right now.
Oh, okay. Fair. So 36, 72 plus 4, that's 76. Great. Now, if you look at this, you would technically have 6 divided by square root of 76 and so on. So now what's happening is, for our formula for curvature, we need the derivative of that, but since these are all constants, we get a 0 vector there. And when we feed that into the curvature formula, which is 0, 0, 0 divided by the magnitude of like another 76 here, you get 0. So curvature of the straight line is 0, which is what we expected. But now we want to try this and find the curvature of something else. So let's see. How about 2D curve? Problem 16. T ln cosine t. I have no clue how much fun this is. I just picked a random problem, so you guys figure it out.
Can you repeat the question?
Find the curvature.
Oh, okay, the K. Curvature.
One. Derivative of t is 1, so you got to multiply by that too. Magnitude is square root of 1 plus 2 squared.
Yes, tangent. What is your weight? I'm
Negative t.
tangent.
I already said that.
You didn't.
What's the derivative of stuff? Yes, derivative of stuff over stuff.
But how? Or really? Okay. Well, that's all I know. No.
Well, natural law.
Derivative of natural law is it's the derivative of the stuff inside over the regular stuff. So it becomes negative sine over cosine, which is
So let me just work this out.
You can't understand the answer.
Cosine squared equals.
No.
Yeah, right, so that.
That's wrong.
One divided
Why
by
are you
secant.
squaring that bad boy?
Because it's one. It's if you're getting one negative tangent t divided by secant square t.
Why are you squaring that secant there, boy? Hang on. 1 plus
Magnitude, right?
1 plus
Secant square t.
is.
Secant square t.
And what do you do when you take a magnitude of something?
Secant squared.
Yes, what's the square root of secant squared?
But then you gotta do it again. You gotta square. You gotta.
What's the square root of a square?
What is k? What's k? It's k is it's t, right? T over.
Magnitude of t prime over magnitude of r prime.
Okay, so that's technically saying this t is also r over magnitude of r prime, right?
Yeah, but shut up.
So it's r prime squared. Magnitude of r prime squared.
Joe,
So it's square root of
wanna
the secant squared.
what?
The secant squared.
I'm always right.
I'm bored.
Yeah, well, I'll just teach you the wrong Still not following but so can r prime be secant? Let's do it.
Guys,
Yeah.
no.
What? Call the presence. As in Grigsby. Oh, wrong? Oh, wait. Yeah, okay. Wait.
That keeps messing me up too. That keeps messing me up.
Yeah, that's right.
There's a big magnitude. I see absolutely. You just mean like cosine?
I just forgot to do the thing. You know, stuff. For my for my t, I forgot to make my sign negative.
Hmm? Oh yeah, this is a magnitude right here.
No, it is.
Right? Are we all getting the cosine t as the answer?
Yeah.
Anyone?
Probably.
$10. All right. All right. It's just a little bit of trig over here, not an issue, hopefully.
Wait, what do you mean? The magnitude? Wait, what do you mean the magnitude?
The derivative of ln is the function goes in denominator, its derivative on top, so you get sine over negative sine over cosine, which is negative tangent. The p hat, which is the unit vector, is the r prime divided by its magnitude, but 1 plus tangent squared is secant squared, square root of that is just secant. And then when you divide 1 by secant, you get 1 over cosine, which is cosine. And you get sine over cosine over 1 over cosine. Cosine cancels, you just get negative sine. So t hat is cosine t, negative sine t. The derivative of that is negative sine t, negative cosine t. And the curvature formula is t prime divided by magnitude of t prime divided by magnitude of r prime. We already know r prime magnitude. We used it for figuring out t. So, and the magnitude of sine t cosine t is 1. So I have 1 divided by secant t, which is 1 divided by 1 over cosine, which is cosine. Now, I said curvature is quantification of how much it curves, right? But you see it's a you see it's a function, right? You see it's a function. So why is it a function? Because depending on where the object is along this path, you have different curvature, which will be reflected in that function. So it curves more here. So that's the higher value of cosine. It curves less over here. It curves the different way, right? For values. Yes?
What are the units of curvature if it were like on like a street or road?
There are no units because it's a ratio of two lengths. The same like radians and degrees. Those are not units. We keep those for convenience, but radian is a ratio of inch over inch, let's say. So it's like a unitless unit. Makes no sense, right? So the same thing for curvature. It's just a number. It's a quantification of how much it curves. This is more than that. That's all it is. Well, we're done with curvature. Clearly dependent on your ability to just shovel functions and take enough derivatives and be careful figuring out the magnitudes and so on. You are memorizing formula for unit tangent vector. You are memorizing formula for curvature. Only 2 formulas. Well, I mean, unit tangent vector was from previous section, not from this one. So technically you only have one new formula to memorize right now, and we are going to learn another one now for normal vectors. By the way, this was a 2D example. What we have, another 3D. So first line was a 3D example. This is a 2D. Just, try another 2D and 3D problem. Principal unit normal vector. Denoted as capital N, hat. You will not see the book use any of these vector notation because they use bold letter and they expect you to know what's a unit vector and what's not a unit vector. but in most textbooks and most of the notation, you will say vector v with the arrow and vector v as a unit with a hat. So that's the difference between the two, knowing that immediately that this has magnitude of 1 because of the little hat on top, which is the unit. So be mindful of those things. What happened? I can. So the notation vector v, unit vector v. That's what I said. You're welcome. So what is this business of the normal vector? Normal vector will point towards the center of the curvature. It's one of the lost arts in education now for you to actually have a compass and draw a circle on a paper. But if you did that, you would have a center and you would use a compass and you would create a circle around that center, and the radius would be the same in all directions. Now, I don't know why I practiced this for a long time and I just didn't do a good job, so let me try one more time. So practice makes perfect, as you can see.
Down in the middle is kind of off.
Get out. The radius is equal in all directions, and what we are going to do now is we are going to see that there is a unit tangent vector pointing in a direction of motion along the parametricized curve. We know that if we are to write our vector as r cosine t, r sine t, we have parametricized the circle where the motion is counterclockwise. So the unit tangent vector must look that way for the point I picked. The principal unit normal vector will be perpendicular to the unit tangent vector, and it will point towards the center of the curvature. It will create the 90 degrees with the tangent vector, which is the reason why we have the word normal in it. Normal means perpendicular, orthogonal. And unit vector, again, it's a unit vector, right? The word principal means pointing towards the center. So now, to understand this even better, if you have some kind of a curve, this is not a circle anymore. So when you parametricize this over the arc length for the pieces that do belong to a circle, maybe over here I can get a piece whose radius, if you are to create a circle that fits the rest of this, right? This is a perfect circle. Your eyes are just bad. So you should check that out, okay? This is the perfect circle. So if I'm looking at the point here, I will have the tangent vector go this way and the normal vector point to the circle. As soon as you move a little bit to the right, there will be a different circle of different size, which also has the center. So these normal vectors are at every point, and any time when you have the straight piece, there is no curvature there. So then the tangent line is actually along the path, and the normal vector will be perpendicular, curvature is 0. So the normal vector is actually the derivative of curvature. So we can understand the normal vector by again, parametrization. This is the arc length. So we have, again, two definitions, one through arc length and then the one that we actually use to compute stuff, which is through T. So definition now. Let R describe a smooth curve parametricized by arc length. The principal unit normal vector at a point P on the curve where curvature is not 0 is given by so normal vector n parametricized by the arc length. Again, this is understanding the concept, not computing. Is going to be the change of the unit vector in respect to parameter s divided by its magnitude, so we can get the unit out of it. Which is 1 over k dt ds. But again, we change this using the parameter t. We have the one step to get it to parameter t, where we just change its so it's a vector quantity, obviously, because it's a unit vector. It should be common sense that the dot product between these two is always 0 because they are perpendicular to each other. So these calculations can take forever because you just have to find so much stuff. So let's have 2D and 3D cases, as examples. So to the example, huh? T squared t, whatever. So try this one. Find the principal unit normal vector for r that is given by t squared and t.
So first, just go like that.
If you have any questions, Ivan and Julie can help. You have a question?
Does that mean that the order of t is like that? But then this is the absolute value of the top. So, but this is what the dash still has. So then take this square root like that. Would that just be? No, but how can you simplify this? That's awesome. Assume tomorrow I lab.
That's done tomorrow, week 2. So one third of the course is done. Actually today, one third of the course is done. Yeah,
Oh, it's incredible. So what's the fastest?
It's insane.
Local one.
You gotta relate MTK something.
Well, that's for the proof. You don't
Yeah.
have to pay for that. Hey, how many times did I invite to that?
And how many times?
The goal is to read
You can do it early or late. Then I have to get this and it show up on
My group is not president of what you was doing. You know my name? You know his name?
Jacob.
I totally stole this seat. Man, you missed crazy stuff.
Goes to Jason.
You're Jason.
Yeah, you were so
I'm
similar.
gonna complain on that one.
Jesus Christ, that's Jason Bourne.
Yeah, I associate him with
I feel like he's also.
like I change it when an actor has a different role. For me, Anthony Hopkins is Hannibal. Like I watched the one Mad movie when he was at the competition. I was waiting for him to go out. So each actor gets one role and that's it.
That's it, lifetime.
Yeah, like that's it.
I don't know. I was just breaking it because I thought that like
No, I knew you. He got so angry. He looked at me and said,
I don't know how to
I'm gonna go see if Julie knows how to do it. He dropped the chair on my foot. Good idea. There's only that guy.
Can you help me appreciate this?
I'm gonna get like, also, it's just my phone charger, I swear.
Wait, how we doing? Is your super long and tedious?
Oh, Alex.
You figured it out?
Yeah, it's not tedious at all.
What do you mean it's not tedious?
I mean, once you realize it, I think it's tedious, but everything has
Oh, wait.
Oh.
Okay, you want to do it?
Oh, wait, no, this
Hey, 65 is tedious.
that's just that.
I just had to use the book.
All right, let's see what we can get here. We start by figuring out tangent vector because that's the root of everything. So I need r prime and then the tangent vector, and also our prime magnitude, which is 4t squared plus 1. Oh, right. So now the unit tangent vector will be 2t1 divided by the square root of 4t squared plus 1. So for our normal vector, we are supposed to take the derivative of t and divide that by the magnitude of derivative of t. That means that we have to find the derivative of this one. So now I'm going to write it as 2t over the square root of 4t squared plus 1, comma 1 over square root of 4t squared plus 1. So this is our vector, unit vector t. And now we take the square root. No, we take the derivative. So t prime is going to be Something, very good. So you can use either a quotient rule or you can use the product rule with the chain rule. Whatever makes you happy. What? Nothing makes you happy? So the quotient rule says that you will square the denominator, take the denominator here times the derivative of the numerator minus 2t times the derivative of this, which is 1/2 4t squared plus 1 to the negative 1/2, and then times the derivative of the inside, which is 2t. That's the first one, comma the second one, which is 1. So we have 4t squared plus 1. Oh, actually, wait, that's just 1 over. So
Wouldn't that be 80? The chain would be 80, right?
yeah, 80. It's hard to see
Yeah, right.
here. Better?
Yeah. Looks square.
All right, so the one on top is 4t squared plus 1 to the negative 1/2. So I'm just going to take that derivative real quick. So it's going to be like this, cubed. There's going to be the 8t on top and negative and 2 over here. I write it this way. I just put the negative 1/2 exponent because it was in the denominator, right?
Yeah.
And you drop the power down, copy, negative 3/2, and then times 80 chain rule. All right, so now we simplify t prime. What do I get? I get 2 square root of 4t squared plus 1 minus this drop minus 8t squared over square root of 4t squared plus 1. Yes. Comma. Oh, this is gonna work beautiful. It's a little bit messy, but it's going to work beautiful. I already see it. And I'm going to leave this as 4t squared plus 1 to the 3/2. Be-
Minus 80 squared is multiplied.
Where? Yeah, well, no, we're going to multiply now by square root of 4t squared plus 1. And that simplifies this greatly. So square root times square root, you get 2 times 4t squared plus 1. Minus these roots cancel, so you just have 8t squared. Divided by, and look, you have the same denominator. Because this used to be, oh wait, I forgot the square root here. So, to the 3/2. and the second one is negative 4t, and you have the same denominator. So now AT's drop, right? When you cancel these guys, all you're left with is that the t prime, it, as you can see, it works beautifully. It's just 2 over 4t squared plus 1 to the 3/2. And then the second one is negative 4t over 4t squared plus 1. So it really simplifies nicely.
So with this T, would you have like a hat or like a vector over? Like a hat, okay. Would we get points off of
You don't need all the points. That's why there are quizzes.
So you should put the hats
All we need to do is to find its magnitude now. But magnitude is a joke because it's squaring. So that's 4 over 4t squared plus 1 cubed plus 16t squared over, again, 4t squared plus 1 cubed, and you get 16t squared plus 4. When you add them, they already have a common denominator, the square root, and if you kick out 4, it goes out as 2. Yes, Alex?
Oh, shouldn't there be an absolute value because you're solving for magnitude around the t prime?
Right here?
Yeah.
Sure, thank you. So when I kick out 4, it goes in front of the square root as 2. We're left with 4t squared plus 1 divided by 4t squared plus 1 cubed. And now these guys cancel. This is amazing how well this works. 2 over square root of 1 over 4t squared plus 1 squared, which is just 2 over 4t squared plus 1. Look at that. Look at that magnitude right there. So now the principal unit normal vector is going to be, where is my t hat?
There's no hat on that one. I'm just worried we might get more points.
Oh, there it is. It takes some time to find it, but so you take this and you divide it by the magnitude. So it is 2 over 4t squared plus 1 to the 3/2, comma, was that negative 4t or 4t?
Negative.
And we are dividing this by 2 over 4t squared plus 1. Now, these guys cancel, right? So the normal vector now becomes 2 and 2 will cancel, and these guys will cancel, leaving us with 1 over square root of 4t squared plus 1. See you next week. All right. And then negative 2 over square root of 4t squared plus 1. It's right there. It's just red. And then what you're seeing here is extremely simple but annoying. There's a difference between hard and annoying. There's nothing hard here. If you learn 3 formulas, you are the master of this section. It's just, how's your algebra? Right? So it's just shoveling terms endlessly and being very careful and hoping for the best, right? And it eventually works, as you can see. So we got this wonderful normal vector having this at one point in life. See that? So, you know, things in life get better. You just keep pushing, you know, keep pounding, and the life eventually gets better. And this is one of the examples of how life gets better, right? With hard work. There you go. Good. I'm sorry? It's annoying, it's difficult. It's, you know, it's not difficult. It's annoying, and it's hard work. It's, you know, you have to, I don't know, hit 50 nails, you know. Yeah. So that was a short 2D example. Are we ready for a 3D? Of course we are. Oh, how about helix? You love those. Ah, all right, helix. Just. So helix. All right, you got this. T. Oh, it looks like L.
What?
L.
It's
Just don't worry about it. It's L.
yeah.
10. Of course you don't.
It's like a music note, but like if you got really tired.
It's a letter L. L. Say L.
Yeah.
Not yeah. L.
Yeah.
There we go. There.
Alright.
See, I'm worried every time I'm like, oh, I know where this is going. That just means I did something wrong.
Yeah, yeah. Yeah, with T and just that.
Get rid of those.
Oh wait, well, this is for like the section supported. Or we can try to jump to here and then the rest after that. That's fine. Okay, so we can jump around. Or if we get out early, maybe tomorrow, something like that. You guys be down, I'll get started on it.
Do we all have the same tangent vector? Yeah.
We talked about the when is the last one we did? Do you have an idea?
Not next week.
Not next week.
Yeah, because we need to cover stuff.
Okay. How'd you get rid of 26? Can you simplify that?
Like this.
Can you simplify that?
No, square root of 121 is 11, and square root of 100 is 10.
You can do, wouldn't you do 2 root of 29?
Maybe. Can I?
I think I'm gonna allow you to do.
So 116 is divisible by 29.
No, by 4 is
116 divided by 4.
29. So you can take
Okay.
this out.
Now let's see.
It doesn't really help your group. It's kind of
Yeah, okay. Okay. So he did. No, it's just got on force, but he did simplify the
Yeah.
radical. I think he was right. Yeah. Okay.
So do we all have the same? And now, as the grand finale, now,
I think that's it.
That is right.
Well, 11 says it. Good enough for me.
all right, that's it for tonight. I will see you all tomorrow.
Question, what feelings are you putting on
Um, 12, 1, and 2.
12, 1, and 12.
Are we doing class tomorrow or are we doing review tomorrow?
We'll try to get both of those.